Let's get started then.
Yeah, okay, let me mute them.
So till Kalpesh shares the screen.
Yeah.
Yeah, thanks everyone for attending. I know we have kind of had lesser participation, but the problem statement is getting more and more interesting as we go. So today we are going to talk about, there won't be any live coding as such today, because what we realized in the last couple of sessions is that it gets a bit monotonous, and we want to cover a bunch of things. So we look at the code though today, and later also look at what patterns we have in some sort of a diagram that will help us talk about the design and critique the design in a better way. So yeah, Kalpesh, over to you.
Yeah, thanks, Chinmay. Okay, so I'm just going through what we have covered so far in first two sessions. So we have implemented first 6 stories, right? 7 stories, sorry, where the initial 3 stories were just the business logic or the initial parsing of the oplog of different types like insert, update, and delete, and we were transforming those oplogs into the SQL statements. Then in second session, we saw the creation of the schema, creation of the table statements from the same insert oplog, and it should be only for the first occurrence of the insert oplog. So that way, we are not generating duplicate create schema and table statements. And then we saw the alter table and the most complex one, which is the story 7, to handle the nested document, which where it was so due to the complexity, we didn't code that live in the second session itself. So I just show you guys the how it can be done, where I show you the existing implementation. So that was the story 7. Today, now as far as story 8 concerned, it is just the reading the oplogs from the file, and the story 9 is the reading the oplogs from the MongoDB. So that means whatever code we have till now, it was just the business logic where we know that there is some source or some from somewhere the oplogs are coming, and we are just processing and transforming those to the SQL statement. So before proceeding, let me show you some a little presentation for the same. So this is our use case, right? Where we are transforming the data, reading the data from MongoDB and transforming it into the SQL statement, and then executing those SQL statement to the Postgres, right? So this is our outcome, where from this oplog we are converting the SQL statements, right? We have done this so far as per our current implementation. But now, what we need to do, that we need to read the oplogs from the MongoDB. Currently, we are just, as a TDD, we are passing those inputs, oplog inputs, to the function. But it is just the business logic we have wrote so far in the main file, right? So today, what we will do, we will write the adapters, like the reader adapter, where it will read the data from the MongoDB or file or any source of the input. And that's where the story 8 comes into the picture, where the story 8 says we need to read the oplogs from the file. So that file may be the JSON file where we have extracted or downloaded from the some running or some MongoDB instance. So we are skipping that as a implementation, so that we will just read the oplogs from the MongoDB. Then we will process those and then generate those SQL statement, post those to the SQL statement, and then there will be a executor who will execute those SQL statement to the Postgres, right? So this is the story. So this is the overall the structure or architecture for the problem. As far as so far we have written all the code into the main, right? So I just wanted to walk through you the existing implementation where how to structure the code basically, where it will be a sequential. So whatever sequential diagram I have shown you, so the code for that is I have just moved the main from the root folder to into the command folder, and the code inside this main is now looks like this, where I'm simply using the Cobra library. I'm sure most of you are aware of the Cobra to write the command line utility, right? So this is easy to create, write the short description, lot description, and writing the help for that particular command. So this part so that application can be closed. We were connection making connections with the Postgres, so we should close those gracefully, right? So this we are handling that interrupt signal here. Next, this is the reader part, right? So this is consider this as a just the interface or adapter, right? We don't know from where this uh, oplogs are coming from. So this reader, I hope this screen is visible enough, right? Font.
Yeah.
Okay.
Should be okay.
So this reader is basically giving me the reader from as per as the input concern, and then once I get the reader, I'm reading the oplogs from that reader and publishing it into the publisher. And whatever publisher I have, so that will be I'm getting that oplog channel in which I will, so all the oplogs will be posted or pushed to that oplog channel. Into that whatever diagram I have shown, right? Once we get this oplog channel, then there is a service, right? So there is a service called oplog service, which will process those oplogs. Now we have these both implementation. I will show you one by one. So first, I will show you the sequential implementation where it will take the oplog channel as the input and process it, and then it will return the SQL channel, right? So if you look at this diagram, yeah, so this is the reader which is posting or reading the oplogs and pushing it to the oplog channel. This is the processor, the service part, and then this is the output SQL channel. And then that this SQL channel, we are passing it to the writer, that is the executor part, right? So this is input, process, and then output. So this is your sequential part. Or data pipeline. We don't know whether it is processing concurrently or sequentially. That is inside this implementation, inside the service. Service is basically the orchestrator. So this is the main. Now, reader and writer, these are the two adapters kind of where I have segregated those into the two separate folders, like reader and the writer. So let's see the reader. So I have created this oplog reader as an interface where the function, there is a single function which will read the oplogs, and then whatever oplogs I am reading, push those oplogs to the publisher. Again, this publisher is something, the interface. I don't know the actual implementation, what is the implementation. And the reason behind creating this interface, because I can now have two separate readers. One is a file reader where we can, as per the input parameter, I can read the oplogs from the file, and the logic of reading the oplogs from the file is here in this function, right? And then for Mongo reader, it will actually connect to the MongoDB instance, and then same, it will publish those oplogs to the publisher. So here I'm getting the data from the actual DB entry and then publishing the oplogs to the publisher. Now, from where I'm getting this data in the main, again, This is the single function where I am deciding which client, which instance I should use. So as per the input parameter, if the oplog file is not empty, that means as a command line parameter, I am passing the file, some file where the oplogs are stored. So it will create the file reader. If not, then it will connect to the MongoDB reader. And where is that MongoDB reader or where it will connect? So that is coming from the configuration. So I'm passing the connection string, and this connection string is coming from the environment variable.
Can you increase font by one more size?
Okay, yeah, sure.
Yeah, thanks. Go on.
Okay. Yeah, so so these are the two readers. Basically, we are reading the oplogs. Same thing is for the writer. There is a configuration, by the way, where we are reading these configuration from the config file, and where it will load the database configuration, Mongo configuration. So all these coming from the .env file. There is a writer. Same, I have created the writer interface, SQL writer, where that writer will be, there is a channel, SQL channel, and it is a read-only channel because we don't, as a implementer, a writer should not write into this channel, and that's why this is the read-only channel, right? So this is the syntax for the read-only channel, and the reason is so this is the interface for the writer, right? And why we have the interface? Because tomorrow I can be write to any instance, like the file writer. Maybe I will generate the .sql files instead of just executing those SQL statement onto the running instance. I can write those to the SQL file. I will just generate the migration files. So this is the file writer for the same, where I will write all whatever generated SQL statements I have. I'm getting into that SQL channel. I will write those into the .sql file. And same is for the Postgres implementation, where I am connecting to the running instance of the Postgres. Again, the configuration is coming from the instance configuration is coming from the config file. And then in the write SQL, I have implemented the transaction so that it will utilize the database connection properly. So this is the implementation for the Postgres. Tomorrow, if business decided that I need to migrate data to MySQL, so I can simply implement this interface and that's it. So I don't need to change anything into the main. So that is the best part of the writing the interfaces. So this is the reader and writer. Now come to the service part, where service is basically just the orchestrator. Now, before going to the concurrent implementation, let's look at the sequential implementation. So this function we are calling from the main, right? So this is the function where we are doing the sequential processing, where it will be
possible to hide the left bar, that way we can see more code.
Okay. Yeah, so this is the, as I said, service is just the orchestrator for your business or the domain, where I'm creating the oplog parser, and you can see that it is inside the domain. The parser is inside the domain. That means our domain or the business logic resides into this parser. And this service is just the orchestrator for it, where where we have this go routine. We are creating again the SQL channel, and then starting one go routine, and then keeping watch on the oplog channel. And this oplog channel is the input. So whatever we are getting this oplog channel from the publisher, right? Where the publisher, where the reader is pushing all those oplogs to the this oplog channel. And here we are reading those oplogs one by one, processing them, and the processing part is into the parser. this parsing or this parser is returning us the all the SQL statement for that particular single oplog, because if you remember in last fourth or fifth story, we are getting multiple SQL statements from a single oplog, like create statement, create schema, create table, and insert statement, right? And if it's nested, then we are getting the multiple SQL statement for the associated tables as well, right? From the single oplog. That's why we are getting multiple SQL statements. And once we get those, we are publishing those again back to the this SQL statement channel, right? So this is the sequential approach where it will process one oplog at a time, and then it will publish those SQL statements to the SQL publisher, and that's it. So this is the solid foundation. So always so whenever we are architecting or designing any system, first implement the sequential or the without concurrent code. Try to complete the functionality. Once you complete the functionality, then make it concurrent. So that way, so whatever code you have written, it is functional, it is fulfilling all the requirements, whatever requirements we have, and then go to the, if required, then only go to the concurrency. Because imagine you have this sequential solution, and whatever and as per the requirement, the data set, whatever data set you are running this utility, that data is not that much, it's a small data set. And with this sequential approach, if it takes less than 30 minutes, and it's a one-time job, right? We don't need this migration to run continuously. If your initial data took less than 30 minutes, then there is no need to write the concurrent implementation, right? But if you are dealing with very large data set, like millions of logs or documents into the MongoDB, then think of the concurrent approach. And in our case, now we are learning, so we are assuming that there is a requirement that we need to process millions of oplogs, existing oplogs, right? So hence this approach will not work, the sequential approach, because it takes a lot of time. And just to give you number, it takes around for 3.6 millions oplogs we have run this sequential approach, sequential program, and it took more than 9 hours to complete the processing. Okay, so 9 hours is too much. So definitely we need to work on this and make it concurrent. Now, feel free to interrupt me if you have any questions in between, okay? So as I said, we need to make a concurrent program, right? So how if we add the worker pool? So that way it is, so what is the workers we need to, we know the what work we need to do, we just the parser. So whatever parser part is doing, it's just transforming the one oplog to the SQL statements, right? And we can, if we have the worker pool where multiple workers will do that same work, the repetitive the work, and then definitely it will be the more performant, right? And but in this case, if all these workers are pushing into the same SQL statement, then it's a bottleneck, right? Because whatever, though there are a lot of workers who are processing and transforming, but there is a single SQL channel and single executor, or there is a single go routine which will be responsible for executing those SQL statements. It's a bottleneck, right? So there is no, so we will not get anything from this adding the worker at this stage only. But so we need to add the another worker pool so that there are multiple workers who can execute those SQL statements into the Postgres SQL, right? But the problem is, if you look at our problem, so we cannot, whenever we are orchestrating the concurrency, we cannot throw any random pattern to the problem. It is more to the, we need to understand the domain very well. In our case, if you look at this, this is the oplog channel where we are getting all the oplogs in this order, right? So order might be anything, insert, update, delete, and then these are the workers who are working on the, so this worker is working on the insert oplog. This is working on the update oplog. And as you know, these workers, we don't know when or who will finish the work first. It is, there is no sequencing here, right? It is very much possible that update or delete will, this worker will finish their work first than the insert, and then we will end up with the migrations like this. The update statement will be generated first, and then insert statement will be generated second. So this is definitely not the correct, right? Because there is no record yet into the DB, and the update statement or whatever state we have, the latest state is not captured into the Postgres DB. So it is not the way, or this is, we cannot use the worker pool directly, right? So while constructing, so in this case, can't we use the concurrency? We can, but there we need to find out the other patterns. Like if you look at the problem statement again, the ordering is only problematic if the statements or or these insert and update or these statements are for the same collection or the same table into the same DB. But what if there is a other DB and other collection into the MongoDB? Then it's totally fine that if update statement for db1.employee is coming before the insert statement of the test.student, right? So there is no dependency or the problem. Sorry, if the database, other database and collection statements are coming before the insert statement of the other database. So it is interdependent, right? It is not dependent on, so if the collection is different, then we can process them parallelly or the concurrently, not parallelly. So how about this design? If again, there is a reader is saying, we are reading these oplogs, and here there is a one go routine who will fan out all these oplogs into the per database. For each database, it will fan out the into the multiple oplogs. So we will have separate channel for each database, and then there will be a separate go routine now who will process and convert those oplogs for that particular database into the SQL statements. And once we go, once it generates this, again, there will be a separate SQL statement per database, and then also executor will be again per database. So this way, we are parallelizing this part of the code without making any issue of the integrity. Data integrity issue will not occur here in this case, because the executing these statements independently per database per table is fine, right? So as I said, it is also fine that we can process these per collection. If you look at, if there is a, if database is same but table is different, then also it's fine that if we have this kind of sequencing. So that means we can process, we can fan out the oplogs one more level, right? Where we can, for each collection inside one database, we can have a separate channel, and hence we can have a separate go routine for that to process those. And then we will again fan in those all the generated SQL statements into a single channel per database, and then execute those SQL statements to the Postgres. We can have these go routines separate per collection for execution as well, but it will be a unnecessarily utilizing resources, because it will open up the connection. So this go routine, the execute SQL go routine, it is opening a separate database connection, right? So if we have a separate go routine for per collection, then, and you have a lot of databases and the collections into the Mongo, then definitely it will exhaust the resource or the exhaust the database connection. So, and it's okay to fan in those per database and execute those concurrently. So we will get the enough performance out of it. And as far as number concerned, so for the same 3.6 millions of logs, this design completes into 1 hour 20 minutes something. So more than 6x performance improvement we saw after in this design in the concurrent data pipeline than the sequential one. Okay. Coming back to
I'll
the
just sort of add some points here. Sorry.
Yeah.
Idea is that we started with, if you go back to the diagram, idea is that if we start with, we want to process n number of databases, and each database, let's say, has m number of collections, right? So there is going to be m into n number of coroutines, which will be running for planning out and processing the oplogs. Later, we'll have n number of only n number of sorry, if you can be on the same diagram, Kalpesh.
Okay.
Yeah, so on the bottom side, on the n databases, there is going to be n number of coroutines. Each coroutine will write to a particular Postgres database, and it will record all writes to all the tables for that particular database. That's the number of coroutines. And idea is to go from a sequential solution. Earlier, we had a single coroutine for parsing the oplogs, reading from Mongo, parsing the oplogs, writing to Postgres. It is all part of a sort of a single, or let's say 3 coroutines, right? In terms of sequential pipeline. Here we are making the whole solution concurrent, and that way we are also able to utilize the parallelism that Go can provide with Go max procs. And if we have n number of databases, n number of collections, we can actually better utilize the resources. That's the idea. I hope Akshay,
Right.
yeah, there was a question from Akshay about explaining the solution one more time. So,
I see.
Yeah.
Okay. Yeah. So as far as resources utilization concerned, so in that design, we have these many Go routines where if we have a separate Go routine for executing the SQL statement as well. So these are the resources wise. We have these many Go routines, that is 4,000. If we have a 16 number of databases, and each database have 128 collections in it. So this is the number. And with our solution, with our optimized core, now we will have just half of the resources. So we have just 2080 Go routines and channels we are using in the final design, in this design.
There is one more question, Kalpesh, which is, does this assume that the collections are known beforehand for every database, or are we spinning up new Go routines based on the collections as they appear in the oplog?
Yeah, correct. As they appear. We have this channel, right? So I will show you the code. I will show you that orchestration. So then we can know that. I'm just minimizing this.
Yeah, correct. To just sort of quickly answer Akshay's question, yes, the database and collections, there is no hard coding in the code. If a new database pops up and a new table or a collection pops up on the Mongo side, a new oplog for that pops up in the oplog collection, a new Go routine will be created for that particular collection database combination.
Yeah, and I will show that how that is handled. So this is our, again, oplog channel where we are getting the oplogs, right, continuously. And in this concurrent implementation, same, we have this parser. This is just the cleanup code where I'm closing all the channels, right? Now here, the only difference is I'm now taking the keeping the record for each database connection. I'm creating one channel, right? Because as per the diagram, right, you can see that in the diagram I show you there are multiple channels for each DB. So this is the map where I'm keeping all those channels. If that channel is not created yet for database, for that particular database, I'm creating a channel and then creating the SQL statement executor for that particular database, and then keeping track of those SQL statement later and pushing back to the SQL channel, and then setting that database channel back to the map, so that so that next time I will not create the database channel again for that same database, right? So this code is execute for each database every time. So whenever there is a new database, and this name is like the I'm getting this database name from the uplog. So whenever that new uplog comes in, and there I have found that there is no database channel created for it, so it creates that database channel here in this code. So I hope that answers your question. So there is no hard coded anywhere into the code how many databases or how many channels, how many collections we are processing. So here in this Go routine, we are processing the collection of log. Now we know that this is the database channel, right? Now we are fanning out again one more level, that is the collection level. So here, same we are doing. We are again iterating. Now this uplog channel, whatever uplog channel we are getting here in this process collection uplog, it is for a single database. There is no there are, so whenever this function will be called n number of times if we have the n number of databases, right? And these many Go routines we have. So this channel is for whatever uplogs we are getting into this uplog channel, it is for that particular database. And we are iterating or ranging over that uplog channel, and then same logic here. I'm getting the table name, that is the collection name in case of MongoDB, getting the table name and checking if that table name or the channel for that particular table is already created or not. If it is not created, then I'm creating that new channel and then processing into the processing that table level uplog here, right? If it is already there, then I'm just pushing, because this channel is already created, I'm just pushing that uplog to that particular channel, same as we did for the collection, right? In the process table uplog, now in this for loop, we are processing the uplog for single table or single collection, right? There is no there is no possibility of getting multiple uploads from the multiple collection or the multiple multiple channels, multiple databases here, right? So once I get the uplog, I'm processing this process log or process uplog function is the same which we wrote, right? In the last live coding session, where if it's insert I, if it's a uplog I, then create the schema, generate the table. This is the recursive table. This is the recursive function we are calling, so that it will generate the SQL statement for the nested objects, right? If it's a update, then generate the update statement, delete statement, and so on. So this is our original uplog processor, where it is processing single uplog at a time. But because we are calling this into the multiple into the Go routines, it is processing concurrently for all the tables. And every time, whenever we are getting this, we are carried forward this SQL statement channel statement object, right? Where we are publishing all the generated SQL statements. And this SQL statement is per database. If you go back here, sorry. We are creating this SQL statement for each database, right? So if you look at this statement, this diagram again, so that channel is this one. For every database, we are creating new SQL statement. So here, it will publish all the SQL statement for that particular database only. All the related statement from that single database will be published to that statement. And now coming back to the main, where we are processing. So because we are creating multiple channels and we don't know how many SQL channels we have created, right? So we have created n number of SQL channels, and that n is not defined anywhere. So it is randomly picked. So that's why we are returning this channel, SQL channel, and ranging over that SQL channel, where for each iteration, we are processing the SQL statement for each database. So if there are n number of databases, then we will have the n number of iterations in this for loop. And each loop, what we are doing, we are creating a writer. Again, this writer is configurable, as I show you, depending on the configuration. If suppose it's a Postgres, then the writer is the Postgres, and it will write those SQL statements from that channel. Again, this get channel is so this SQL statement is having a DB name and the separate SQL channel for each DB, where I'm passing that SQL channel to writer SQL, right? And just show you the Postgres. So this is that SQL reader channel where I'm ranging over the SQL commands and executing all these commands in the onto that Postgres connection, whatever connection I have created. And I made this transaction just for optimizing the performance, right? If we are executing these statements separately, so then it is not that much performant, because writing and committing or flushing the actual data to each command, it is not performant one. So what I did, I'm creating the transaction here. At the beginning, I'm creating this transaction, and then have this batch size. This is again hard coded at the moment, but we can configure that into the configuration file. So currently I have set this as a 10,000. If once that 10,000 statements are reached, then it will commit that transaction and then start the new transaction. So this way, we are efficiently using the Postgres database connection. Right. And this is the service part, and whatever parser I have, so it is in the domain. So domain will have all the business logic, which I already shown you, right? The processing part, and then other domain objects like oplock entry, where this oplock entry object structure is there. Same is for publisher, where I have created again the interface for the publisher, where today I'm using this in memory publisher, right? But tomorrow, if I wanted to replace that with some other publisher, like maybe Redis or Kafka or some messaging system, where I will publish those messages and then subscribe those messages or the oplogs, so I can have that implementation. So that's why I created this interface. There is a need of writing this UID generator interface to write the test cases, because in the test cases, we are generating if you remember, we are generating the UID for the primary key into the associated tables, right? And this is the implementation where we are just using this one library, go fake it, which will generate the UID. But in case of test, if you use this code into the test, then this will generate the random UID every time, right? And it is difficult to write the test cases for that. So what I have done, so in the test, I'm creating the stub generator, stub UID generator. This was the default UID generator, right? Which is implementing this interface method. But in the test, I have created this separate structure called stub UID generator, and it will always generate this stub ID. If you observe that in the test case, I will in the expect output, instead of the actual UID, okay, sorry. Yeah. So instead of having the UID, this will always have the stub underscore ID for the associated queries. And this is specifically for the writing the test cases purpose. Otherwise, there is no way to assert these output with the generated output. Yeah. Apart from that, same for the cache. I have created the interface where tomorrow I can change. Currently, I'm using the map from the sync package, so that I don't need to manage the synchronize for synchronizing purpose. I'm using this. Otherwise, I need to write my own mutex lock and unlock every time whenever I'm getting or writing key into the data map, into that particular map. So I'm using this inbuilt sync.map, which will handle the synchronization for you, so that at a time it will just one writer and maybe multiple readers. And let me show you the test for this concurrent implementation, how to write the test. All right. So that is again one complex problem. So same, we have this oplock channel, right, as an input to the our orchestrator function. So this is our orchestrator function for which we are writing the test, correct? Process oplocks concurrently. So input is oplock channel, and then it will generate the SQL statement channel. So same way we wrote other test cases, so I have created this as a function, so that way it will be readable. Otherwise, it will make the test very complex. I will show you the what I'm doing here, but assume that this function will be returning some channel which will have the oplocks. And what is the expected output? So it expects all these statements: create statement, create schema for test, create table for student. Then there is another table called create table test.employee, right? But because this function is concurrent, we don't know which one will come first, right? Whether it's a test.student, the queries will be coming for test.student first or test.employee, right? So we don't know that sequencing because of the concurrency. So how to test that part of the coding? Remember, there is we cannot check the exact ordering because there is no guarantee of the order whenever we have the concurrent code, right? So how to write test cases for the same? Uh, we are so while writing the test cases, always check for the correctness, and order doesn't matter in case of the concurrent code. So which one is executing first, that is not matter. And when I say order, it is not the order for a single table. The order is for the multiple tables, because this ordering we already tested during our the previous test cases, right? We have covered those where update statement will be always come after the insert statement for that particular database. So that test cases we already wrote. But here it might be possible that these two statement for test.employee, it will be processed before the student table, right? So as output, I will get these two statement as a first statement, and then later I will get these create statements for the student, right? So that is where I'm referring to the when I say the ordering here, not the ordering for the single table, right? So This is the uplog service. I created object, called that concurrent function, getting the SQL channel. I am first doesn't generated the SQL statement which I was expecting. So that test will fail here. But if number of SQL statements are same, then next we need to check whether those SQL statements are correct or not, right? So inside that, what we are doing, I'm arranging over the want the for each SQL statement, I'm ranging over, and inside that again, I am have a separate for loop towards the whatever SQL statements I got from the actual function call from here. So if that is found, then I'm just breaking this internal for loop. If it is not found, that means for this SQL statement inside the want, there is no statement found in the got SQL. That means the error got failed. So this is how we can write the test for the concurrent code. Any questions on this?
Yeah, there are no questions right now.
Right.
Cool. So I guess what you can do is quickly summarize where we came from, from a sequential implementation to concurrent. We show a performance graph of what we have observed so far, and what could be the next steps. There are a few stories that we did not cover, probably left as an exercise for people who want to write out.
Sure. Yeah, so we saw this sequential data pipeline, right? Where we are reading a single part. So first we have wrote the code story-wise, where we implemented the business logic, which will parsing the individual uplogs like insert, update, and delete. So once we have the solid foundation or the business logic done, then we started working on the orchestrating part, where from where these input or for this domain, from where we are getting the input and where we are sending the output. That is the input and the output part, where we wrote the separate reader and writer interfaces, where tomorrow if we wanted to implement the another implementation as adapter, then we can easily write the implementation for the same. But once we have the sequential data pipeline, as I said, always try to do not start writing the concurrent code at the first place, right? Well, if it is required, then only start the concurrency. Otherwise, if your work is done with the sequential data pipeline, then prefer that one. But as I said, if your business or whatever domain you are working on, it is asking you or forcing you to write the concurrency code, then first you should evaluate your sequential data pipeline like we did. So for 3.6 million, it took 9 hours, 20 minutes of time to process those many uploads. Then we started thinking on the orchestration part of the concurrency, where we thought, let's assume, or how about if we implement the worker pool, right, for processing, because it's the same work we need to do to just translate one upload to the SQL segment. But as per the business logic or as per the domain, we cannot do that because of the data integrity issue. It will be generate the data integrity issue. So we cannot use the worker pool. Then we explore the other database, other concurrency patterns, where we are fanning out and fanning into the system. Again, we saw that we just fanning out and processing those into multiple go routines and having a single go routine, it is a bottleneck. So again, it is a challenge of the concurrency. So we need to think of that, and it is again domain specific, where we can have a concurrent code for this part as well, to execute the SQL statement on the Postgres. So we came up with this design. Then we identified that so this improves the performance a lot, but still it was taking 2 hours 18 minutes for when just fanning out the uploads per database. Then we go deeper again into the problem statement, and then we identified that though we can again fan out these uploads per collection, so that is also not an issue if we concurrently execute those uploads for each collection. So we came up with this design where it will have n number of databases. So we will fan out those many upload channels, and then for each database we will fan out to number of if there are m collections into the each database, then we are again fanning out those uploads and then processing, having the separate go routine to process those, right? And then having separate SQL statement channel, SQL channel, and then go routines for each SQL channel to execute those. But then we identified that there are too many database collections are happening with the database, which is not it make performance, but it is making it very slow because of this number of database connections happening at a time. All right. So we optimize that part here, where we have the SQL channel per database and not for the per collection. And as far as this performance concern, so in the initial sequential design, it took 9 hours 20 minutes, and for the final concurrent data pipeline, it took 1 hour 36 minutes for 3.6 million number of uploads. So this is all about how to design, how to write the test TDD, and then orchestrate your concurrency. Next stories are like there are story number 10 and 11 as well, where story number 10 says bookmark support. So this bookmark support is basically right now, if we run this utility, it will start reading the uploads from the beginning, from the MongoDB. And if we stop this utility in between, then and we restart this again, it will start from the beginning, because there is no bookmarking or there is no state where we are maintaining how many uploads we already processed. So that bookmarking feature is not there into the current solution. But as an exercise, maybe you can attempt to solve this or add the bookmarking support. Then story 11, which is distributed execution. So right now, this utility, we are running this utility into as a single instance, right? But we can, what if we have multiple instances ran for the same utility? Maybe say, for example, in Kubernetes, you have spawned this as a multiple pods, and this utility is running into the multiple pods at the same time. We cannot do with the current design, because if you look at this, we need to make sure that all the instances will read from the same MongoDB, right? And they don't know each other, which upload is already run or already processed by which pod or which instance, right? So we need to maintain that state as well. So these two things are kind of good exercise for you to attempt and solve. So yeah, feel free to solve these two stories.
Okay, thanks, Kalpesh.
Yeah, I think.
Yeah, so this concludes our series on
yeah.
system design with Go. we'll hopefully have a few more coming our way. We have another problem statement that we are working on, which is implementing 0.1 version of Redis. And there is upcoming problem that we are currently working on, which is implementing something like Grafana Loki, 0.1 version of that. So look forward to conducting more of these sessions. And if you have any feedback, please feel free to share that. We'll share the feedback link later.
Yeah.
Yeah. Thanks, guys.
Okay. Thank you.
Have a great time. Keep learning. Bye.
Thank you.